Raise your hand. Okay. Yep. Okay. I'm David Rindskopf from City University of New York. Not NYU, they have more money than we do. Now we're here to talk about the exciting part, which is the statistics, right? Yeah, deafening silence. Okay. I know that there's only one test that single case design researchers approve of. Does anybody know what that test is called? Have you heard of the intraocular traumatic test? Intraocular traumatic test. So the difference is so big it hits you between the eyes. And that's what everybody hopes for with single case research, that they'll get a difference that's so big that you can't ignore it, and you win the Nobel Prize and everybody's happy. But unfortunately, it doesn't always work out that way. And the effects aren't always as obvious as we'd like them to be. And as Rob mentioned, government agencies and journals and associations have developed standards for presenting things in quantitative form, so that you don't just say it's a heck of a big effect, or it's a whaling effect, or it's a huge effect, or something like that. You have to actually put a number on these things. So I've been interested in issues of how to do it. And I'm going to tell you either later this morning and more into this afternoon about some complicated ways I've thought of doing this. But lately I've been thinking about simpler ways, because I think although complicated ways are nice, and it's nice for people who are statisticians to know that there are these ways to do things, the actual researchers are going to fall back on simpler ways and want easier ideas easier ways to quantify things. So I've been working on some simple variations of things you probably have seen before, and I know most of you, I don't know that most of you have seen them, I know quite a few of you have seen this, the article from which this slide comes. I can make it a little bigger so you can see the parts of it. Parker and Van Est, and Parker and Associates, 9 overlap measures. So I'm going to talk about some overlap measures and what's right about them, what's wrong about them, and can anything be done to make it so that it's a reasonable thing to do to use these kinds of things. So the problem is no overlap measures can be absolutely perfect for a simple reason. If you imagine in most of these methods, you'll see 2 lines drawn on the picture. In fact, I've got one of them. We can hand out these so that you can all look at least at one of these while you're so you can look at one of them. It'll be this one, E, on the left-hand side there. Somehow, you've got a vertical line which obviously divides the phases. So you've got a baseline and a treatment phase, and then you've got a horizontal line which divides the points into high scores and low scores. And if you ask yourself what would be a perfect relationship, it would be if all the points, in this case, the treatment is supposed to increase whatever the behavior is. So that the perfect thing would be to have all the points on the left below the line and all the points on the right above the line, and that would be a perfect relationship. But then you could have, if you imagine a group of points in the lower left and in the upper right, you could imagine taking the upper right and raising it more and raising it more, so that there's more and more a distance between the control or baseline condition and the treatment condition. And as you increase that, the degree of non-overlap doesn't change because they didn't overlap in the first place. So as you make that bigger and bigger, you don't get a bigger effect size. So there's nothing that can deal with that issue. But it turns out that over a wide range of values, there are some overlap measures that perform fairly well and others that don't. So if you now think about this, and when you're looking at the page that's handed out or something, what criteria do you think there ought to be for these estimators, for these measures of effect size? If you want to have an effect size that you can get relatively easily without many calculations from a graph like this, what would you do? What would your criteria be? Something that statisticians think about a lot, but other people don't think about at all, is does it estimate a parameter? Is there some underlying value that you want to estimate that this does a good job of estimating? So statisticians think about this all the time. Ordinary people don't even realize it's a question. So the other thing that I thought about for something like this is it comparable to other measures, like the typical parametric measures? You think of an effect size. Does everybody know what a standardized effect size is? So that if it's been usually used not in single case designs, but in between group studies, where if you got one group, you got another group, you've got some difference in the means between them, but how do you know how big that difference is? 5 points, what does 5 points mean? Who knows? So you divide that difference by the standard deviation either of the control group or the average of the control and the treatment groups. So you get a number of standard deviations that they're apart. So it'd be something like this. You'd have two groups. If it wasn't single case design, you'd have two groups like this, and there'd be some distance between the middle of this group and the middle of this group, and you'd express it in terms of number of standard deviations. So that's a standardized effect size. So one of the things I wanted to do was to get something that was comparable to that, because that's what everybody uses in the meta-analysis field. Everybody compares effect sizes that way, and if we want to get single case design studies into the mainstream, we'd have to have something that was at least somewhat comparable to an effect size like that. And then you want something, obviously, for single case design researchers, they don't want to calculate at all, right? You don't want to do anything with numbers, so that, but I can't say we'll do nothing with numbers, but I'd like to minimize it, right? Have as few calculations as possible for you. And think about, do these things really measure non-overlap? Like if you look at the one you have, which is this one, where is the horizontal line drawn? That's at the median of the baseline phase, right? So you've got 6 points in the baseline. So it divides the top 3 points in the baseline phase from the bottom 3 points, right? So if you think of that as dividing the points, the horizontal line and the vertical line, dividing the points into 4 regions, and you're counting the number of points in each region, and it's kind of like a crosstab, a little 2x2 crosstab, how many points are in each part. What you'd like to do is have a measure which has all 6 of the baseline points in the lower left and all 7 treatment phase in the upper right, but you can't do it with this. You can never, if you draw the horizontal line at the median, you'll always have half the baseline points above, half the baseline points below. You can't get a perfect relationship by certain measures. So measures like this, to me, won't work. What would you do to cure that? You might think it would be something like the non-overlap measures like like PND and PAND. Right? Where you pick the high point of it. But you know, most of you know, if you've read this article or critiques of these measures, that basing it on where one point is could be an outlier. The top point in that phase could be an outlier, could throw things. It's very sensitive to outliers, so you don't want to do that. So what I thought of was to do something that's not illustrated on here at all, is you count up, right, how many points do you have in this baseline? You have 6 points in the baseline phase. So you go up 6 points. Here's over all the phases. Here's 1, 2, 3, 4, 5, and now the 6th is a tie, so you could either put the line here, or just under, or just over. And that's a way that if there were a perfect relationship, you would have it, and if there's not, you won't falsely have a perfect relationship. So I want something that'll get a maximum value for a perfect relationship, but won't otherwise. So some of these methods have problems with that. How many of you have seen this article from which this comes? Yeah, nearly half of you. Okay, so anyone who took the single case design course basically saw this article. So what I wanted to do in this is to get a quantitative estimate that's comparable to that standardized effect size D. And something else which you probably don't see in many of these. Does anybody remember in reading this article, did they talk about the standard error of any of the effect sizes and a confidence or a confidence interval for them? There's not much in there about standard errors and confidence intervals. So those of you who are not quantitative people may wonder, why do I care about that? What does a standard error tell you about an estimate? Standard error tells you how accurately you've estimated something. And if the standard error is small, you've estimated it accurately. And if the standard error is large, you have not estimated it accurately. And with the sample sizes that you often get in single case designs, estimates of many of these quantities would probably not be very accurate. And you'd want to know that through knowing what the standard error is, or in the case of some of them are based on a slightly different logic, like, let me see, if you, here it is down here. There's one called NAP, which essentially says compare all the cases in the baseline to all the cases in the treatment. And for each pair that you get one from one and one from the other, you see which one's higher. And then you see, of all those, what proportion are higher in the treatment phase than in the baseline phase. So it's essentially, it's a very nice number to get for interpretation. it's the probability that a point in the treatment phase is higher than than a point in the control phase. And that tells a lot of people something about what they need to know with that, but it's a non-parametric measure. It's really not estimating anything in particular, so it's harder to get a confidence interval on that. So that's a little different. But all the rest of these are things which you might be able to get a standard error or a confidence interval for. And you really need those to tell how good a job that measure is doing. So I wanted to get D as standard error. I wanted it to be simple with very little calculation. I wanted it to be based on overlap, even though that's not perfect. As I said, non-overlap can occur